First of all, I just would like to express my acknowledgement. Thanks for the organizers who invited me and then given a lot of support to be able to enjoy the very exciting conferences. And also the rest of my talk are actually a collection of all the efforts combined by the huge number of the teams, or the project teams, Tanpopo, Hayabusa 1, 2, and the Solar Power Cell Working Group and Life Study Team. I'm sort of summarizing the major portion. To start, I think a couple of days ago we had say classic Drake equation and then how bad it is and how good it is, but I didn't go for that. But I just want to make this as a usual sort of guideline of astrobiology disciplines. In my opinion, the FL and NE and FP and NE and FL, those three parameters, which used to be sort of just a philosophical thing, but now it's down to the scientific foundation. We can discuss about it. So I'm not saying Drake equation is not omnipotent, which is not, but we as a scientists should be able to tackle how rationally we can derive those three parameters. And then, in terms of space missions, I don't know why all the fonts are different from my original, but anyway, now the astrobiology can be done on Earth or via telescope and then in the space. When you say space, anywhere outside the Earth, but for us as space scientists, we have to be careful about where the space you're talking about. So we're starting off on the very close vicinity, low Earth orbit, and then small bodies of the solar system, and next planet, and then a little bit farther down, and then next planetary systems. So today, since limited time, I just concentrate on three because the Mars has been well described by Jean-Pierre, and exoplanet, you just hear that one lecture before me. So the low Earth orbit and the small bodies, and then ocean world. Those missing parts are what I'm trying to cover. Okay. Low Earth orbit. So what we're going to do is we have a set of the International Space Station where we can receive micrometeoroid impacts at hypervelocity regime, though. And also, we do have artificial junk space debris, inevitably. But by having those particles collected relatively intact, and then you can actually do meteoritical analysis and then judge where those particles come from. So this is not new. This has been done by the LDF period in space shuttle era. But now we take the advantage of having Japanese facility on ISS, and then called Tanpopo, which represents dandelion, the flower, which seeds blown in the wind and then spread the seeds to the other part of the world. So we set this as a very first astrobiology experiment derived from Japan in space. Basically, it's both exposure experiment of microbes and artificial organics, or astronomical organic analogs, and micrometeoroid capture intact, wherever possible. And to try to say some portion of, it's not entire, but some portion of lethal panspermia or chemical evolution hypothesis. Subdivision is that we have a microparticle captures and then space exposure experiment that might tell you about interplanetary migration of life precursors or life themselves, and organic compounds related to, so these are two life and life precursors. Orbital debris and apparatus, these are technological things. So in order to do so, we need to have both capture experiment and exposure experiment. For the exposure ones, of course, it has to be all terrestrial origin, but nevertheless. So ISS has the three axis gravity stabilized attitude control. That means one face is always facing towards the velocity vector, one face always facing towards space or opposite to the Earth. So that by choosing carefully which area you want to expose your collection media, then you can quickly do some orbital analysis that the space pointing phase preferentially receive micrometeor. In other words, it's very difficult for the Earth orbiting object to reach it. So for the space phases, preferentially micrometeor capture, and then a velocity vector mixture of orbital debris and the micrometeoroid. We do use aerogel, which has become famous for the Stardust mission. But we have a 0.01 gram per cc or 10 milligram per cubic centimeter bulk density, which is the lowest density ever flown in space, like here. So that way, the maximum heat temperature at the time of the hyperburst impact on the surface of the micrometeoroid could be minimized. It's not really too gentle, but nevertheless, it's the best we can get. And for the exposure experiment, we have a small cells. It's the same fashion as a European exposed experiment on the Columbus module, but each of them has a small inlet. You can put whichever microorganism, extremophiles, or organic compounds. These are just a short list of what we have flown, like Deinococcus rhododendrons to start, and some others for the microorganism. And then artificial organic compounds and glycine, the isovalines, and hydrogenthiones, others, alanine, and also possible powders. So then these are all now once exposed in space in duration about the year, and then retrieved back to the Earth. We actually that's just a normal exercise, but the difference from the previous similar experiment is that Tanpopo project has flown everything at once, and we can continue up to 4 years. So each year we will retrieve back the fully 1 year exposed aerogel and a set of the organics and the microorganism exposure experiment for the first duration of 1 year and 2 years, and lastly 3 years, so that you can see a survival rate or a degradation rate annually. So that started in 2015. And then exposed facility here by using robot arm, and this Japanese shoji-looking area. This is what aerogel is exposed. And then we are just about toward the end of first 100-day initial sample analysis period, towards end of this year. And we now have the first publication to be ready in astrobiology soon. So what we had was after returning in September this year for the first year sample, and the second year sample is still on orbit and being exposed now. It's retrieved back to the ISS my facility in very simple clean room, and put into encapsulated to each cases. Looks like that. So this is what came back from the Earth, from space, and then encapsulated for the dedicated inspection system. And also this is simple X-ray tomography captures images, and then you can see a little particle impact craters. This is actually the preview, because this is the very first conferences I've shown this, because we are still working on the very initial analysis sphere. So I don't tell you any numbers or any findings scientifically, because I have to write the papers for it. But as you can see, this is sequential images of the trucks. Starting from here, and then gradually coming down, so it's underneath the surface, subsurface, and then that's where all the terminus particles and residues are kept. The other one, this is so-called the bursted track. Both of them can be were actually observed in stardust samples as well as previous aerosol captures. But this may be a relatively a strong meaty particles which can survive towards the end. And then for those ones are more fragile or less cohesive particles, such as chondric porous particles. And then we do have those poking glass needles to actually dissect the individual aerosol into such small area in same fashion as what people did for the stardust, without losing a single particles less than 10 microns, and looking like that, and then just pull out by the machine. And once we extract them, we start to do the so-called detailed analysis. That's going to happen from next January by 26 different institutions over Japan. So we are distributing the particles, for instance, this of the thermal alterations to assess how much they are or how intact they are. Or this is, I think, that Yoko's and her colleagues work about concentration of the organic compounds, just to name a few. Okay, so indeed, we can do something about astrobiology very close to the ISS. But once you go further down, we are talking about different discipline of the astrobiology, that is life precursor, or search of life precursor, or bring them back to your laboratory. So that's cometry and asteroidal sample return missions. The Hayabusa was one of the first parallel to the Stardust mission. For the Hayabusa in 2003 to 2010, that was the very first demonstration of ensuring verification of the sample return from the microgravity body surface. We made three major science discoveries. One of them is we have solved so-called space weathering paradox. Was actually indeed by nanophase iron on the top of the surface by return samples. And then we also have discovered there is a granular migration in such very small gravity conditions even. This is like closest image of the touchdown site of the spacecraft right here. And if you blow up, this will be blown up like this way. Now a scale bar is about 1 meter. So that those rocks are probably as small as or as big as your head. So and then the smallest pebbles you can see is about a few millimeter. So this is no longer astronomical picture, it's more like a geological picture. And then I can even blow up over here. This is how we look like. And these are the areas we actually received the samples from. And then backsides, these are actually the final image, thank you, of Eros by Nia Shoemaker. So you can see the grain size or granular size are far different on the even pond of the microgravity surfaces. And this is a pavement of NASA facility. So in this, all the same scale. And then surprisingly, those smooth terrain follows the gravitational potential, and so we actually see the apparent avalanche features from the pictures, but that feature perfectly matches with geopotential low area. So that was our first discovery that indeed the particle actually migrates on the surface of microgravity, and actually even by looking at those normal gases analysis of receiving of the galactic cosmic ray, the individual particles actually go submerge and ascend in different epochs, individual of them. And then we did a microtomography of individual particles, and you can see that though some of them are eroded and rounded, and some of them are sharply edged and freshly cracked. So there, and then no wonder, because the touchdown site both the mixture of smooth terrain and the steepest terrain of the asteroid right next to it. So it has a mixture on that. So we are also able to say something like that. And also, once we studied about those vesicular features of individual particles, and you can see the minerals, and you know that how much temperature you melt the minerals. Therefore, you can actually presume that what's the minimum internal temperature of parent body of Itokawa. So by having both remote sensing and sample analysis, you can actually have a total genesis of a asteroid. We'll do the same for the Hayabusa 2 with different asteroid. Now it's on its way, and then it'll be to 1998 GU3, or now we know the Ryugu. This is actually a C-type asteroid. So now it's a reservoir of hydrated minerals and organic compounds. So supposedly we arrive in mid-2018 and stay 18 months and then hopefully come back at the end of 2020. So these are sort of roadmap where we are heading to, and then now we have a good friend. The American friends are going to the similar carbonaceous asteroids in different target at almost the same time. Then what's next? We want to go further down. Especially, we want to go to D-type asteroid or Jupiter Trojan we haven't never seen before, because those are the beyond snow line. And then, of course, not only Trojans are one of those exotic asteroids, but also that has a clue of how true or the possible planetary migrations taking place in our planetary system. So that there's a competing hypothesis of a classic origin of the Trojans, just remnants of leftovers of building about Jupiter. That was old view, and now present view is actually present-day Jupiter Trojans that actually migrated second generation from the farther down in the Kuiper Belt area. So in order to do so, we have to go there and do some census. That's a new frontier theme for the United States. But for us in Japan, we are not as strong rocket as they have. So we decided to have one detailed study of one well-known asteroids. So how are we going to do? We'll have a solar cell and ion engine, which has been demonstrated already. So we combine these two and then bring this up to go there. Takes about like 12 years to get there though. And then go one of those 20-kilometer size asteroids, hopefully in a D-type. And then making like hopefully at the edge of the survivors. In other words, it's a long period, survival period, and then do some infrared imager to find the landing site and land it there. And then we may have those sort of embedded weathered area and a freshly excavated area or downsloped area. And then we'll see if those constituents are rather similar to comets or rather similar to asteroid. If they are similar to the comets or Kuiper Belt, then probably migration theory will have a strong evidences, or vice versa. So that we have lander and taking heritage of sampling from Hayabusa 1 and 2. We do have some sampling devices, but before going back to the Earth, now we do now in situ mass spectrometry under development in Japan, and then collaboration with France too. So the targeting mass resolution is something like 20,000. So it's more like 100 times more accurate than the Cassini. Thank you very much. So probably I just have to really go quickly ocean world and then take some questions. So what's next after reaching to there, and then there's one final study you can do for the astrobiology by the mission is habitability and possibly second genesis. Of course, now we know large paradigm shift of those habitable zone, the surface habitat to deep habitat underneath of those icy satellites. And then we start to see the plume of the Ceres plume and the Europa plume of Enceladus. And then we had a good talk about Enceladus yesterday and the Titans, but let alone the Europa. So for the case of the Enceladus, probably I don't have to explain this to the audiences. We have a chemistry and we have global ocean directly connect to the rocky core. That's an important thing. And now the Japanese experimentalists actually somehow supported evidence of the discovery of Nano-Silica can be reproduced by hydrothermal vent at the surface of the bottom of the sea. So then, since 5 years ago, we are discussing with the American colleagues that is there any possible way we do this? But of course, discussion we had, what's a biomarker yesterday? We don't know. So the second best thing is that we just bring the samples back and then we think about it in laboratory to do many different tests. So of course, it's a very far away. It's like five times farther down the Hayabusa would go. And then the sample we'll get may not be direct evidence of the second genesis, but it's most likely a chemical markers, and less likely all the biological signatures, or we may sit somewhere between. But actually, it is important to examine each level. It's very difficult to do that in one single instrument in like 2 kilograms or 3 kilograms can be on board a spacecraft. So, of course, we tried the best for those mass spectrometry, which we'll develop in solar cell, but it's also important to have sample return. Okay, to do so, we have to have flyby sample return. That's actually developed by Tanpopo. And then hypervelocity impacts and microgravity study are actually done by the Hayabusa 1 and 2. And however, that's one big thing that when we bring the samples back, it's a planetary protection issue, which you have to do. And then that's actually the take-home message. When we have to do the receiving facility on the contingency plan. We have to study from now. And in fact, as from this year, there's a European project called PPOS. Planetary protection of outer solar system has started, and Japan and the United States are a member of it. So together with this heritage of space missions and the new challenges of planetary missions, hopefully we would like to have water drop from the different planets, or I mean, different world. Thank you very much.